instead of in the standard metropolisting, you basically your move always go to where it's more likely, right? That's the whole idea. But the problem is that when the chain running early stage, sometimes it just attract all these local modes. So what Tuck's idea was, well, why don't we do the reciprocal of the usual metropolisting ratio? So basically, you will purposely go to places where it's actually low. And the idea is this way, in order to converge, you need to diverge first to explore the space. But then, of course, you need to come back. So that's the paper as we talk. David and I worked. Now, talk how many years ago now? Must be, I don't know, 6, 7 years now.
Yeah,
And
it has been long time.
a long time. Okay, long time. And then Tark joined, Penn State, and I think Tark, you can tell the rest of the story. How do you start working with Sid? But we're really, really happy to hear you guys have been pushing this to the really next frontier, and so this is definitely of great interest. And we also, statisticians always admire physicists. I can say that openly, particularly in these computation problems. I'm really glad that we have real physicists here to work with us. So Tuck, you want to say a few things?
Oh yeah. So CZ and I worked on it for a long time, for about 5 years. Basically, C took the idea of repelling attracting and applied it to Hamiltonian Monte Carlo from scratch. He did a lot of work to make it happen, and I hope you enjoy the new advance of Hamiltonian Monte Carlo.
Thank you. Ted, it's all yours. Welcome.
Excellent. Thank you so much for the invitation to talk. I think Shaoli gave a really great introduction that I don't think I really need to spend that much time introducing the problem because I don't think I can say it better. But just to add a little bit to the context, so I think this whole project started after when Tuck had just joined Penn State and he was giving a similar sort of lunch seminar for us over there, and I'd asked him a question about the repelling-attracting that Shaoli had mentioned, and we wanted to sort of investigate how you can use the geometry of the problem itself in order to make it more efficient in high-dimensional spaces. So that was sort of really the motivation for this, and um, we never started off considering Hamiltonian Monte Carlo as the right framework for this. We were looking at other methods, and it turned out that this was um, the most efficient way of extending the repelling attracting framework to higher dimensional sort of multimodal distributions. So this was sort of the background for how we got started on this. Okay, so this is a quick sort of I'll just flash the QR code over here. But if you want to follow along with the slides and maybe asynchronously look at something else, you can do that and scan the. Okay, all right. So I want to spend maybe just a couple of minutes just setting the stage for the setting of the problem that we're investigating, and maybe just a bird's eye picture for what the sort of main contributions are and what the motivation is. Okay, so the setting is we want to generate samples, say Q1 through Qn from some target distribution pi, and we sort of assume that pi basically has this negative log PDF that we're going to refer to as the potential function. And this is a sort of classically very well studied problem in statistics, and particularly more recently in sort of more modern machine learning methods. So there's been a plethora of different works that are interested in investigating this question, right? So it starts off all the way back to rejection sampling, and then you have the Metropolis Hastings random walk Metropolis, and you can sort of add on to that by considering the gradient information that underlies your target distribution. And this gives you variants like the Metropolis adjusted Langevin algorithm and Hamiltonian Monte Carlo, right? And so these are sort of the methods where you are generating proposals and then running it through a Metropolis.
Siddharth,
Yes.
quick question.
Yes.
So the Langevin algorithm that I'm familiar with is more of a diffusion process, right? So
Yeah.
how does it work in this case, and what happens?
Yeah, so in this case, you just take the Langevin stochastic differential equation, and then you do the Euler-Maruyama scheme, and then you take one step of that Euler-Maruyama scheme, and then you sort of run it through the Metropolis Hastings filter, where you accept or reject based on a certain probability ratio. So you do a Metropolis adjustment to the classical Langevin algorithm.
Okay.
Yeah.
Right. Thank you.
So I think it's also more frequently abbreviated as Metropolis adjusted Langevin algorithm. So you might see it in literature referred to this way. Yeah. And so we're not entirely restricted to this framework if we're interested in just generating samples, and there are other more modern methods like that sort of approach this problem from a variational perspective, where you look at it as optimization on the space of probability measures. But for this talk, I will sort of we will be interested in this framework where we are sort of generating exact samples from this target distribution. Okay, so the classical random walk Metropolis, so this is sort of like an illustration using basically this excellent template that Chi Fong has created online to sort of visualize these samplers. And if your target distribution is, in this case, say, strongly log concave, then the random walk Metropolis is going to do a really good job in sampling from this distribution, especially if it's in low dimensions, like two-dimensional target distribution that you see over here. Okay, but when your target distribution sort of gets more complex, the standard random walk Metropolis is going to have a hard time generating proposals in low density regions. And as Shaoli was mentioning, this was sort of the initial motivation for the RAM algorithm that was proposed by Tuck and Shaoli and David Van Dyke. Okay, so in order to overcome this sort of a situation where you have complex geometry, so we'll look at the example over here, and the sort of go-to framework in most statistical implementations of the shelf Markov chain Monte Carlo algorithm is the Hamiltonian Monte Carlo, and it's sort of auto-tuned variant, which is the no U-turn sampler. And essentially, the framework over here is that you're going to sort of create a dynamical system and generate proposals. So your transition kernel is going to be the integral solution of this dynamical system. So this is an example of what would happen if you were to implement Hamiltonian Monte Carlo in the framework of this problem. And as you can sort of see that Hamiltonian Monte Carlo is going to have a hard time in this situation generating samples that move from one mode to the other. So it has a hard time moving across low density regions. And this is something that is sort of, so we'll discuss it, but this essentially has to do with the fact that when you look at the problem of sampling through the lens of Hamiltonian Monte Carlo, you're going to look at the negative log density of your target distribution as the energy function. And when you have low density regions, these are effectively high energy barriers that you have, and sort of generating trajectories which traverse isoenergy contours are unable to sort of overcome those sort of barriers. So the proposal that we have for overcoming this limitation is, so this is sort of like a bird's eye view of what I'm going to be talking about for the rest of the talk. So it's sort of the underlying objective over here is you're going to sort of generate proposals where for the first half of the trajectory, you move from high density regions to low density regions. And then for the second half, you're going to go from the low density regions back to the high density regions with the underlying objective to transition from one mode to the other, or in other words, transition across high energy barriers, right? So if we sort of run this framework for a little bit longer, this is sort of what you're going to see. Okay, so I think this is a good point for me to stop and ask if there are any questions.
One perhaps one quick question: what are those black trajectories that are being drawn over there?
So the black trajectories are the trajectories that the methodology is proposing. So
how do you decide where it stops?
Yeah, so I will so the as we proceed through the talk, I will describe exactly what's happening over here.
Okay.
Okay.
Any question here? Okay.
I'm sorry.
Sorry.
Were there questions?
No, I said there's no question. We're waiting for the magic.
Okay. Yeah, all right. So the high level objective is we want to design a sampler that can efficiently sample from multimodal distributions, and it preserves all the nice properties of existing mainstays. So when I say mainstays over here, I particularly mean Hamiltonian Monte Carlo. Okay. All right. So the sort of well-known issue with random walk metropolis is that essentially this is generating a sort of diffusion in space. And if your target distribution has some lower dimensional structure, like what you see on the right-hand side over here, it's unable to adapt to that. So it's going to end up wasting too much time in high dimensional space trying to explore regions where there really is no sort of information. So the Metropolis adjusted Langevin algorithm, or Langevin Monte Carlo in general, as I mentioned, this is basically just the Euler-Maruyama discretization of the Langevin SDE. And so this is going to generate proposals that are based on one step of this discretized diffusion over here, right? And then you're going to run it through this Metropolis Hastings filter. And this gives you, well, theoretically, it gives you a much sort of better adaptation to the geometry of the problem, right? But this comes with its own issue where it's incredibly sensitive to the step sizes, because you're essentially just taking one step and then doing an accept reject decision process. So the way Hamiltonian Monte Carlo sort of overcomes this limitation in the Langevin diffusion is to essentially say that, okay, we're going to augment our state space where we want to generate samples from Q. We're going to now add this additional dimension to our state space by considering these momentum variables P that are more often than not assumed to follow a Gaussian distribution. And you're going to look at the extended state space, which is also called the phase space over here, as the target distribution in the phase space. You're going to look at the negative log density of that as the Hamiltonian of a physical system, and you're going to generate proposals by solving this system of differential equations. So you integrate the ODE that you see over here. So this is an autonomous ODE. So you integrate that for time t, and whatever you end up with, you accept or reject that with a certain probability, right? So the accept reject probability over here consists of three crucial terms, right? So the first is basically the ratio of the Markov transition kernels that you have. And then you have the ratio of the target distribution at the proposed state and the initial state. And then because you're generating proposals through the solution of this ODE, there's a Jacobian correction term that you need to account for in order to make sure that the target distribution is a valid probability density function. Okay, so there are basically these three main components that you need to sort of take into account if you want to look at any differential equation and generate samples from that as a Markov chain. Okay. So if you were to do this, you sort of have proposals that are better adapted to the geometry of the problem, and this is sort of well known. And as I had mentioned, this is sort of the most commonly used sampler that you would have in any sampling software. Okay, so the four main reasons why Hamiltonian Monte Carlo is as effective as it is attributed to these four properties that I'm going to talk about. So the first is something that's very, very well known about Hamiltonian systems, which is the conservation of energy. So essentially, if you look at your trajectories along the flow of the Hamiltonian system, the energy along this flow is conserved. So the change in the Hamiltonian along this flow is going to be zero, right? So this means that anytime you stop your dynamical system and say, okay, I'm going to stop here and take a proposal from this state, that's going to give you something where which is going to have exactly the same target density as the place where you started off from at time zero. Okay, so effectively what this is saying is that when you generate Hamiltonian flows, you're traversing isoenergy contours in your phase space. And what this allows you to do right now is the ratio over here, this becomes 1 because energy is conserved. So you don't have to compute that ratio if you want to sort of compute this acceptance probability over here. Okay, so this is good. The second point about Hamiltonian Monte Carlo is the reversibility, and essentially this sort of goes back to a result by Tierney that says that if you want to use a deterministic Markov kernel for generating proposals from a target distribution, then for it to be reversible, or for it to satisfy detailed balance, it has to be an involution. Okay, so essentially, our proposal over here is the time t flow of the Hamiltonian system, right? And the time t flow by itself is not an involution, but if you augment it with this momentum flip operator, which essentially just takes your position and momentum q and p, and then it just flips the momentum. So if you were to augment it, then it becomes an involution, right? So this is now saying that, okay, I can satisfy detailed balance, but it also says something more, which is if you were to look at this acceptance probability, these terms over here, they also get canceled because they're both identically 1. Okay. So now the only term that remains is this Jacobian correction term. And the third property of Hamiltonian systems is that it preserves volume in your phase space. So if you were to look at the determinant of this Jacobian term, this is always going to be 1 for any time t on your flow. So now even this term over here, this becomes 1. So effectively what this is saying is if you know exactly how to solve this Hamiltonian flow, then for any sort of target distribution, you can just generate the exact time t flow, and you don't even need to run it through this accept reject step in order to generate valid samples from your target distribution. All right, but solving the exact time t flow for this Hamiltonian system is saying that, okay, I need to know exactly how to solve this at time t, right? So it implicitly depends on your target distribution over here. And for, any sort of arbitrary target distribution you're given, the time t flow for that is not necessarily going to be available to you. So we have to rely on numerical schemes and numerical discretizations. And in order to do that effectively, the fourth property of Hamiltonian Monte Carlo and Hamiltonian flows is this property of symplecticity. So what this sort of result over here is saying is if you look at this symplectic 2 form, so essentially it's if you were to look at your phase space and you look at infinitesimal displacements, so dq and dp, which are sort of essentially infinitesimal displacements in your position and your momentum. And if you look at the parallelogram that is spanned by, the pairs of qi and its conjugate pi, if you look at the areas of those parallelograms and then you add it up across all dimensions you have in your space, this is essentially your symplectic 2 form. So it's a signed area that measures for every point in your phase space what is the sum of the areas of those parallelograms. And the Hamiltonian flow conserves the symplectic 2 form, right? So you can sort of see that the preservation of volume is implied by the preservation of the symplectic form, but the property of preserving the symplectic 2 form gives you access to certain geometric integrators, right? And in particular, it gives you access to this leapfrog scheme, which is incredibly efficient in sort of numerically solving your Hamiltonian ODE. Okay, so the access of these symplectic integrators is available because of the fourth property of Hamiltonian flows, which is the symplecticity. Okay. So the leapfrog scheme essentially says that, okay, this is so these are the two equations in the ODE that we want to solve. So for a time discretization epsilon, what we're going to do is we're going to take a half step in the momentum, and then we're going to take a full step in the position, and then another half step in the momentum. And essentially, we're going to compose this L times to give you the time t flow phi t, which is approximately phi epsilon times L. Right? So essentially, if you want to generate the flow for time t with a step discretization epsilon, you look at t over epsilon, and you call this L, and then you generate this numerical scheme L times, and this gives you the symplectic integration for the Hamiltonian flow. Okay, so so this was a really quick introduction to Hamiltonian Monte Carlo and what makes it so successful in practice, right? And the importance of symplectic integration is that the following theorem, essentially a culmination of different works in 30 years, has really studied the geometry of these symplectic integrators. And essentially what it says is that if you look at the error introduced by choosing a numerical integration scheme as opposed to the exact integration scheme, this is of order epsilon squared, right, for exponentially long trajectory links. And the implication that this has in the problem of sampling is that if we know that the numerical scheme closely preserves the continuous time dynamics, then the accept reject probability that we're going to compute is at least e to the minus epsilon squared. So this is what it sort of guarantees. So as I decrease epsilon, I'm sort of making my numerical integration more precise. And because I make it more precise, my acceptance probability is going to be closer to 1. And if I make epsilon larger, then I will have numerical integration errors. But the fact that this is a symplectic integrator tells you that it's strongly controlled by how small your accept reject probability.
So can I ask a question?
Yes, yes.
Yeah, we just try to get a little bit intuition. Thank you, this is wonderful, the overview. The original, when you start to set up the Hamiltonian system, statistically speaking, you have P and Qs are independent of each other, right? Because the two problems. Is there what's the intuition there? Is that's the best scheme because of physics? So could one think about something correlated with each other? Would that just always worse?
Yeah, that's an excellent question. I think the sort of the analogy from physics is that if you want to consider them to be a Hamiltonian system, then the position and the momentum have a very sort of rigid interpretation where you're going to look at the momentum as being a dual variable of your position. So over there, like from that perspective itself, there's this sort of sense of orthogonality that exists. But if you were to look at it from a purely statistical standpoint, I don't think there's anything preventing you from sort of looking at Q and P being sort of correlated with each other. But I think the only sort of issue that it might introduce is that ultimately, when we sort of run Hamiltonian Monte Carlo, you're going to have samples of Q and P, but you can completely marginalize out the P by just disregarding it, and now you end up with your samples from Q.
Yeah.
Disentangling that when you start off with correlated variables is going to become a little bit more tricky.
I see. I was just wondering whether, kind of typically when you have a physical interpretation, that usually the nature does optimal things, right? I wonder whether there's a mathematical results here saying you can put in any correlation you want, but according to some criteria, the best one will be the orthogonal ones. Fits the physical reality. Is there such results?
I mean, that's a very intriguing perspective. I don't know of any such results. I mean, it is true that you can sort of look at this Hamiltonian formulation as
Yeah.
like this principle of least action for like Euler-Lagrange equations, right? And I wonder if you introduce correlations over here, what implication they will have in the variational formulation. And then perhaps you can argue that it's optimal to have them independent of each other. But this is not something that I am aware of. So I don't know if I'm qualified to give you an educated response about this.
Well, you certainly know far more than I do. I'm just curious if it's not optimal, that suggests there's something even better, right? Because this is already pretty good.
Right. But that is a very interesting question. Yeah, I don't know.
That would be a thesis for some students.
Right. Yeah.
Thank you.
Are there any other questions? So I was sort of told that it's a more relaxed setting, and
Yeah.
and usually it sort of goes on for longer. So I don't know if I'm going too fast or too slow, but feel free to interrupt and sort of ask questions along the way if you have any.
You're doing perfectly.
Right. Okay. So, so I've just sort of given you all of these sort of excellent theoretical properties that Hamiltonian systems satisfy, and therefore the Hamiltonian Monte Carlo inherits by virtue of being intrinsically related to the Hamiltonian system, right? So is HMC the panacea, right? Is this as good as we can possibly do? Right? So I this simple example over here hopefully will sort of illustrate where there is room for improvement in HMC. So over here we're going to consider this bimodal target distribution. So it's just an equally weighted mixture of two Gaussians, and the means of these two Gaussians is basically it's on two opposite sides of a hypercube in RD, right? And we're going to choose an initial state that is in a sufficiently high density region of your first Gaussian. So Q0, Q0 is going to be closer to the negative mean as opposed to the positive mean. And how close it is quantified by this parameter delta. So if delta is closer to 1, that means Q0 is in higher density regions. If delta is far away from 1, that means it's closer to the sort of equidistant point between the two nodes. And now we're going to define this event E. So E depends on your dimension and the location of the means of your two Gaussians. So so the event E is basically the event where after running your Hamiltonian Monte Carlo for time t, right, so your Hamiltonian flow for time t starting from q naught. So E is the event that you're closer to the your second mode as opposed to your first mode that you started off from. So you start off from a mode that's closer to negative b, and E is the event where you end up at time t at a mode that is closer to the second mode. And now we can ask, what is the probability of this event? How often does this happen? Because ultimately, if we want to investigate whether Hamiltonian Monte Carlo is able to jump between modes, we need to know what is the probability of transitioning from one mode to the other. So it turns out that this probability is given by this result over here. So if you take delta to be sufficiently large, so I will sort of mention what the sufficiently large over here means in just a second. Okay? But what I'll point out is that if delta is large, that means you're closer to the higher density region around your first mode. So if delta is sufficiently large, then the probability of even generating a proposal that is closer to the other mode is decreases exponentially in the dimension. So it decreases exponentially in the dimension. And this quantity over here, that's delta b squared over 2 sigma squared. And this is something that sort of captures the change. So the main term over here is the exponential dependence in the dimension. Right? So if you go from b equals 2 to b equals 3, the probability of generating proposals itself from one mode to the other is sort of sharply decreasing.
So Sid, is there a magical value here make the exponential part 0, or that delta is not allowed? I don't mean to make 0, make it 1.
Delta 1?
Oh, no, sorry, make the 0, right? Because and that value is not allowed. It's a delta.
Well, so technically, yeah, you're right. This actually can be delta 1. So you can have delta 1 where you can say what happens if you start exactly at your mode.
No, I was asking whether, I mean, look at the expression of the exponential. You can make the exponential part independent of d, right? By making delta equal to, 2 sigma squared divided by b squared or something. But that value is not allowed, right?
Yeah, well, so over here you're sort of looking at what happens for a fixed b and a fixed sigma, right? So you're saying, okay, you fix your parameters of the Gaussian. How does that depend on dimensions? So as you can sort of see that b over here is independent of your dimension because you're always in a hypercube, and it's just like the scale of this hypercube is controlled by b.
Okay.
So this delta sufficiently large is required to sort of rule out cases where you can have, say, a mixture of Gaussians that look like this, and now if you're sort of closer to this mode over here, then it is possibly very likely that you'll make a transition from this mode to this mode, right? So delta sufficiently large over here means that you're relative to sigma, you are in the high density region that belongs to the one of the modes. Okay? So that's what this condition delta is saying over here. Right? But the main sort of takeaway over here is the exponential dependence in the dimensions. So more transitions. So just observing a transition is incredibly rare in high dimensions. And this is not telling you anything about what would happen to the accept-reject probability, or having an accepted state which is closer to the second mode. Right? And all of those are going to be even rarer than this. Okay, so this is sort of like.
Can I ask a quick question, Siddharth?
Yes.
So it seems to me, I mean, so if this presupposes that you know the values of B, right? And if you don't know that, would this, how would you use this information?
Yeah, so usually in the sampling setting, you know what your density is, what your target distribution is up to normalizing constants. Right? So over
Yeah.
here, E and sigma are things that you ideally know beforehand.
Okay. Now, I'm reminded of the time delay problem that Tak was working on, and I believe that the modes could be sometimes very, could be separated by a large amount. And I mean, Tak can probably say more about that. But so if a given analysis produces, many such modes, then you want to jump between them.
Yeah.
What would your strategy be? I mean, how would you choose the D, perhaps?
Uh,
So in a time delay problem, we had very well separated modes. I mean, separated by very large zero density region.
Yeah.
So in this setting of see the example that is close to sufficiently large delta. If delta is sufficiently large, the modes are well separated by huge zero density region. And in that case, this example proposition shows that typical Hamiltonian Monte Carlo cannot make a transition often because probability of transitioning from one mode to well separated the other mode is exponentially decreasing to zero. So this is the drawback of the typical Hamiltonian Monte Carlo, and Seed is proposing something new to overcome this situation. So yeah.
Got it. Okay, thank you.
so, so this is sort of what you would see if you generated proposals from some region. Most of them are going to stay within that vicinity of that node. So that's what the previous result was saying. Okay, so this sets the stage for the repelling-attracting HMC framework that we proposed, and essentially the main observations over here are the whole methodology just boils down to two simple, embarrassingly simple observations. So the first is that friction decreases energy along a flow. Right? So what we mean by this is if you look at the trajectory of a particle, but that is now subjected to some frictional damping, this is what your uh, sort of differential equations are going to look like, where this additional negative gamma t term, gamma times pt term that you see over here is the sort of constant linear damping that is happening because of friction. So we can rewrite this as a Hamiltonian ODE in this following form. Right? So the only difference, so this is the usual Hamiltonian ODEs that we were looking at previously. The only difference is that there's this additional term over here. That's the damping that is introduced by friction, and this gives you the sort of concise representation over here, where um, uh, this is the contribution of friction. So this differential equation over here, or the Hamiltonian system that this dynamics belongs to, is known as a conformal Hamiltonian system. So this is well studied in the physics and mathematics literature, especially because this has real world implications, and if you want to sort of model systems where there is a specific amount of loss or damping that happens, you would want to use differential equations that take into account damping that happens because of friction. So this is a well-studied object, right? And if you were to incorporate this additional friction term into the Hamiltonian flows, what you're going to see is the sort of visualization that you see on the right-hand side. So on the left-hand side is the traversal of the isoenergy contours, which is sort of characteristic of Hamiltonian systems. And if you introduce friction, then it's going to sort of slow down and ultimately settle in the modes that you have. So the sort of visual interpretation, or I guess the sort of physical interpretation to keep in mind over here from the perspective of mechanical systems is that these modes are sort of like poles that you have, and effectively you have a particle that's sliding on a rough surface, and then eventually, after as your time goes to infinity, it's going to sort of slowly settle down in the bottom of that pole. And this is sort of what the visualization on the right hand side is demonstrating. Okay, so now what we thought was what would happen if you just flip the sign of the friction parameter. So instead of having positive friction, which is damping the system, if you just flip the sign of the friction parameter, then instead of having a dissipative system where you're losing energy, over here now you're sort of gaining energy as time progresses along your flow, right? So this isn't going to change the geometry of the problem. So what you're going to end up with is still a conformal Hamiltonian system. The only difference is that there's this plus gamma times your state, your position and momentum, which is different from the minus gamma term that we saw. So the addition of this gamma times your phase variables over there is going to lead to gaining or accrual of energy. So if you were to look at what this would mean in terms of the trajectories, so this is what you see. So on the left-hand side is your standard Hamiltonian dynamics where you're traversing isoenergy contours. On the right-hand side, you just flip the sign of friction, and now the modes that you had are suddenly more like repelling states. Any questions about this?
So this, I assume this negative friction does not exist in reality? Mathematics exists, but it doesn't exist in reality at all?
Well, so it I was trying to sort of see if there was some sort of like physical, maybe like quantum mechanical analogs to what this would mean in the physical world. I don't have a convincing answer to this that it exists in reality, because this would have implications on things like the entropy only increasing. So in this case, the entropy would always decrease, and that
Oh, I see.
the arrow of time that you have is sort of related to the direction in which entropy is increasing. So I really don't know. I'm not sort of qualified enough to sort of talk about whether this exists in physical systems or not, but I think for the most part, it's safe to say that this is definitely not in mainstream physics.
Well, it'd be fun.
So I was thinking, obviously, that I don't think this actually exists in physics, but it made me think about how, when you're at the airport and there's like the moving walkways.
Yeah.
It's like speeding you up in the direction you're going, kind of.
I
like
see.
that.
Well, that exists.
Yeah, that's not the same thing, because like that could actually be modeled and this can't, but it made me think of that.
Yeah, this is sort of like at the beginning of those walkways, and then towards the end it kind of slows down a little bit, and that's the positive friction term. I think that's a great analogy. So what this means is that your particle is suddenly gaining more energy and is accelerating along the flow as opposed to decelerating. And this is sort of reminiscent of repelling dynamics. So basically,
Now, there is also the expansion of the universe.
Yes. I don't know if that has to do with anything related to friction.
No, but it's just an additional term in the equation.
Okay. Yeah, that's a good point. I would have to see if there's some way of talking about this through the rest of the expansion course. Right. Uh, so our sort of proposal is basically to combine these two types of dynamics. So we choose a friction parameter gamma and a friction time t, and then for the first half, we're going to generate dynamics through negative friction. So your modes become Repelling states. And then for the second half, we're going to flip the sign of friction. And now the second half is the conventional friction that we all know. So this is going to simulate attracting dynamics where the modes become attracting states. And you do this for the first and the second half objectively. And now you can sort of accept or reject your usual metropolis systems probability. So you have your ratio of the transition kernels, you have the ratio of the target densities at time t and time zero, and then you have the Jacobian correction. So, so, so before I sort of talk about I guess, the theoretical aspects, this is just some illustrations of what the repelling attracting dynamics would look like, where you're transitioning across modes.
It just looks cool, even just in the video. I mean, it looks really cool. Now, Sid, I think I asked Tuck this question, but I forgot the answer. The choice of the half is it theoretical driven or it's just a convenience? So
It is the choice. So when you say half, you mean the t by 2?
yeah, right. Because it doesn't have to be, right? At least mathematically.
So I will make some comments about that as I describe
Okay.
but it is necessary if you want to do it efficiently, right? Because ultimately you can use this result over here, and uh, uh, this result over here says that you can generate any dynamical system, so you're not restricted to t over 2, as long as you compute these these terms over here, you have a valid Markov chain. So in that perspective, the t over 2 is not necessary. But if you want to sort of get better efficiency, then you will have to use t over 2, and I'll sort of talk about that a little bit when we discuss the results shortly. So now I'll just sort of quickly go through the theoretical aspects of this. Maybe I won't dwell on it too much. But the main points are that the repetitive tracking, right? So this dynamics is time reversible. So if you apply your momentum flip operator, so essentially what this result is saying is that the momentum flip applied. Uh, so if you flip the momentum and then you run your repelling dynamics, that's the same as going backward in your attracting dynamics and then running a momentum and then doing a momentum flip operation. So in a certain sense, these two uh, sort of repelling and attracting dynamics are conjugate to each other, but they're only conjugate with respect to the momentum flip operation. So if you don't do the momentum flip operation, right, then if you just run the backward dynamics after running, so let's say you run repelling and then you run attracting from the repelled state, it's not going to bring you back to where you started off from. You have to perform a momentum flip and then do attracting dynamics if you want to come back to the place where you started off from. So this was a particularly interesting result. But what this allows you to sort of now say is that, okay, when the composition of your repelling and then attracting dynamics, along with the momentum flip operation, now gives you an involution, right? So based on that result by Tierney, this constitutes a Markov kernel that satisfies detail balance. So the reversibility property holds over here. And of course, the ratio of the transition kernels that you have in your acceptance, your accept reject ratio, that sort of gets canceled out. The second result is that if you look at what happens to the volume in your phase space, for the first half of your trajectory, your volume expands. Okay, so your Jacobian is increasing for the first half, and for the second half of the trajectory, your Jacobian is decreasing, so there's like a volume contraction that is happening. But if you look at it at time 0 and time t, so this is time 0 and time t. So if you look at it time 0 and time t, this Jacobian term is exactly 1. Okay, so when you go back to the accept reject probability, you don't need to compute Jacobians, which are incredibly expensive. This is guaranteed to be 1.
So then see, this is a point where Shaoli's question arose, because if it is not half of the time, then your volume expands, but then it doesn't shrink correctly. I mean, to the same point. So the Jacobian may not be equal to 1 if it is not half of the time. Is it the point?
Yeah, that's exactly the point. So you need to compute Jacobians if you want to do it for something that isn't 1/2. You need to compute Jacobians, but the sort of more detrimental aspect of not using 1/2 is that it violates reversibility. So you don't satisfy detail balance, because what this result over here is saying, and thank you for pointing that out, Tuck, because I may have forgotten to mention this, is that the reversibility property holds only when these two are equal, right? So these two times have to be equal to each other. So I need to run forward dynamics for the same time as I run backward dynamics for this condition to hold. So you won't have detail balance, but that isn't a necessary condition for you to have valid samples, but it definitely violates the detail balance condition if you don't have t over 2. Okay, so we have reversibility, we have preservation of volume in the phase space, and it turns out that we also have preservation of symplectic structure. So if you look at your symplectic 2 form, essentially, as with the volume, there's an expansion that happens in the first half of your trajectory, and then in the second half of your trajectory, there's a contraction that happens. And when you choose exactly a time capital T, you have that your symplectic 2 form is preserved. So what this means is that now it gives you access to numerical schemes that are known as conformal symplectic integrators. And in particular, there's the conformal symplectic leapfrog that was proposed by Franza and Mike Jordan and René Vidal in this really interesting paper that came out in 2020. So that is given by the scheme that you see over here, right? So even though it looks like this is more complex than the leapfrog, right? I'll just quickly point out that the inner 3 steps that you see over here, these are exactly the leapfrog steps that are happening over here. So it's only those 2 outer steps that is the addition of the conformal symplectic leapfrog. And essentially all of those are don't require any gradient evaluations. So it's not going to significantly increase your computational time for implementing this method. Okay, so we have reversibility, volume preservation, symplecticity. Unfortunately, the situation is a little more bleak when it comes to energy conservation, right? And in general, it doesn't hold that energy is conserved, right? But if you are willing to make some assumptions about your negative log density, then essentially what you can say is that if you run your forward, if you run the repelling attracting dynamics for time t, and then you look at whether energy is conserved between your final state and your initial state where you started off from, this is bounded by this quantity that you see over here, right? So essentially, this comprises of two terms. So this first term is sort of e to the negative lambda times the time that you're integrating it for. So essentially, if you integrate it for longer, in a certain sense, this gives you better approximation control. And there's this additional term that you see over here, and this is the maximum of the differences in the Hamiltonian that you have, only evaluated on the critical set of your energy landscape. Okay, so all of your modes are essentially points where the gradient evaluates to 0. So this is definitely the case where you have well-separated singular modes that look like bumps. But this also takes into account cases where you have what are known as generalized modes, where your modes can be lower dimensional manifolds, like it can be a density ridge, for example. And this is saying that, okay, this works even in these cases, but there's this additional sort of bias that you have in your energy drift. That is the maximum of the differences that you have in your Hamiltonian evaluated on the critical set. Okay, so if you further assume that your distribution is strongly log concave, or equivalently that your potential energy function is strongly convex, then you can show that, okay, this energy drift that you have is bounded by some constant. The constant is a small constant. Okay, so in terms of the actual computation of the accept reject ratio, there isn't, oops. There isn't much else that you need to do apart from looking at the differences in the energy, right? So looking at the energy drift that you have. And unlike the classical HMC over here, this doesn't tell you that it's exactly 0, but that it's, you know, at most some quantity. Okay. So, so we did a couple of simulations over here to see how much can the energy drift in different sort of situations. So in this case, we're looking at a high-dimensional mixture of anisotropic Gaussian distributions, and we ran the simulations for different simulation lengths L, different values of your friction parameter gamma, right? And in most cases, right, you'll see that, you know, the energy drift is not significantly different from 0. And that's sort of what you see in the box plot on the right-hand side, where your energy drift, it's not exactly 0, but it's sort of tightly concentrated around 0.
So the question about energy drift is, okay, so once you have any drift, you will incur additional computation to compute the ratio, right? The original, because energy drift, you don't have the ratio at all. So is there a little investigation here as the trade-off? Because this requires, in terms of the gain, obviously there's a gaining and there's a little bit cost. What is the, is there some way to argue this trade-off is definitely worthwhile?
Yeah. So hopefully maybe when I talk about the experiments, maybe it'll sort of I can hopefully make a case that that trade-off is worthwhile. But as far as energy drift is concerned, one thing that I'll quickly mention is that even in HMC, the vanilla HMC, you need to still compute the the ratio of those energies. So even though I said that we can in principle cancel them out, we can only cancel them out when we know the exact time t integrator. So when we use
Oh,
numerical schemes, we still need to do that computation.
I
But
see.
the fact that your energy drift in the conservative Hamiltonian case is zero tells you that your accept reject probability is lower bounded by something. So if you choose smaller step sizes, then you're going to have higher acceptance probabilities. So unfortunately, in this case, I cannot make a similar guarantee over here, where your accept reject probability is bounded below by e to the minus this quantity that is on the right hand side.
Got it. Thank you.
So it could potentially uh, sort of have meaningful effect on how many samples you're how many proposals you're accepting. Okay, and the last sorry, was there another
Oh,
question?
uh, so in this case, the energy drifts. In a traditional HMC, it will get higher acceptance rate, but it will be for unimodal exploration. In RAMC, we lose that strict bound. Strict bound by exponential bound. We don't have that, but so we end up with smaller acceptance rate. But this one is for exploring the complicated geometry of the target distribution. So I think there's trade-offs. Yeah, as Charlie mentioned. Yeah.
Yeah, that's exactly right. And maybe I'll sort of try to talk about the acceptance rate and the effects that we saw when we did the simulations. But before I go into the experiments, the last thing that I'll mention is that just like the usual Hamiltonian Monte Carlo, because this is a conformal symplectic integrator that we're using over here, you have the same approximation error. So the numerical scheme approximates your continuous time dynamics up to order epsilon squared in error for long trajectories. Okay, all right.
One thing I also want to mention in the previous slide is that here, so the only computational overhead is the outer stage, and those are not that expensive, meaning that RAMC's computational time is almost identical to traditional HMC, but it can also jump between modes. And it also can sample the unimodal cases. And I think Sid may mention that how much more effectively RAMC can sample unimodal cases.
Yeah. Okay. So, uh, so I'll talk about a couple of experiments that we did. Maybe I'll go through it slightly quickly, and if you want to come back to any of them in detail, I'd be more than happy to. So the first one is basically so I selected two of a couple of other controlled experiments that we that we had run in the paper. So in this case, I'm highlighting two different scenarios. So the first one that you see on the left-hand side is a classic benchmark situation that was considered in the energy sampler paper, where you have a collection of different it's a Gaussian mixture model, and you want to sample from that. What you see on the right-hand side is something that we constructed just to sort of illustrate this generalized mode phenomenon that I was talking about, right? Where your modes are now supported on the boundaries of these nested L1 balls in R2, right? So essentially, if you sort of zoom in, hopefully you can sort of see the target distribution better, right? So you have 4 smaller L1 balls, and then you have 1 larger L1 ball. Your high density regions are supported on those diamond shapes that you see over there, right? And the reason why we considered this setting, the reason why we considered the setting over here is that most of the sort of multimodal solutions that exist in literature deal with the case where you have these small bumps as modes. So there's usually like an inner optimization routine that is run inside your sampler, where the optimization routine hopes to find modes, and there's some cache in which the existing known modal locations are stored, and then you sort of generate proposals from a standard like Metropolis or Hamiltonian Monte Carlo type kernel in combination with the knowledge of the existing modes that you've received. So there's like an exploitation sort of trade-off in a lot of those models, right? But restricting yourself to only looking at modes that are sort of these sort of isolated points in space can be incredibly inefficient, where in this scenario, if you were to look at isolated modes, that actually is an infinite set, right, that you see on the right-hand side. So that can be very inefficient. Okay, so we looked at a couple of different comparisons, right? So the first one is the RAM paper by Tuck and Shaoli and David Van Dyke. And then there's the pseudo-extended Hamiltonian Monte Carlo, right? And essentially the main sort of insight of the authors in this paper is that you can look at your extended phase space, and then you can look at like Cartesian products of tempered versions of this extended space, and hopefully, if you have modes, they sort of intersect in those Cartesian products. The one main drawback about this pseudo-extended Hamiltonian Monte Carlo framework is that if you have a high-dimensional problem, looking at Cartesian products of high-dimensional phase spaces can become ultra-high-dimensional, and that sort of takes a real hit on your computational time. And then the third method is the wormhole Hamiltonian Monte Carlo that was proposed in 2014. Okay. So this is a quick highlight of the results over here, right? So the main sort of metric that we use throughout our examples for assessing the quality of the samples is the Wasserstein metric over here, right? So in particular, we use the Synchron divergence, because in all of these scenarios, we know exactly what that target distribution is that we need to sample from. And if you look at the Wasserstein metric, you can sort of see that there is, for the benchmark data set, which is the mixture of Gaussians, there is a sort of a noticeable decrease in using the repelling-attracting dynamics as opposed to just vanilla HMC. Right? And because it's a low-dimensional problem, RAM performs competitively in this case, and so does the wormhole Hamiltonian Monte Carlo, which essentially, as I mentioned, does really well where you have isolated modes in your space. And now when you move from a problem that has isolated modes to one where you have these generalized modes, high density regions on manifolds, you'll see that the repelling attracting dynamic still does well, and so does RAM. And RAM does well because it's not constrained to, a certain definition of what it means to be a mode. But the wormhole Hamiltonian Monte Carlo does really badly in this case because it sort of gets fixated on one particular sort of high density region and is unable to explore the other aspects of your space. Okay. So in terms of the acceptance rates, you'll see that it's sort of reasonable and is more or less in line with the other methods. The overall computational time is more, but it's more because we use a sort of nested dual averaging scheme for choosing the step size and the simulation length. And what it sort of automatically tunes it to be is, much larger than the same procedure for HMC. Okay, so essentially the difference that you see in the overall CPU time is purely attributable to the fact that you're taking more steps for a single proposal in the repelling attracting Hamiltonian Monte Carlo. But if you sort of divide it by the number of steps you take to generate a single proposal, you'll see that it's basically, the same order of magnitude as HMC. Okay, so this is sort of a quick scatter plot on how these methods perform, where you have the repelling attracting on the top right, you have HMC on the top left, you have RAM on the bottom left, and you have the wormhole Hamiltonian Monte Carlo on the bottom right. So ideally, you would want to see frequent hopping between modes, right? And for the most part, all three methods that aren't HMC achieve this. But if we were to look at the trace plot, you'll see that it happens a lot more frequently with this sort of repelling attracting framework as opposed to the other two. Okay, and this is sort of a scatter plot of the concentric L1 balls. Okay. So the second experiment, we consider a mixture of high dimensional and isotropic Gaussians. So you'll see sort of the covariance structure on the left hand side. Essentially, like the main sort of hardness of this problem has to do with the fact that your eigenvalues or the sort of the eccentricity of the ellipse that you have of your covariance matrix is getting squished, but also the directions of your principal eigenvectors are perpendicular to each other. Okay, so what this means is that it's easy for you to jump from this mode to this mode because this is the direction of the principal eigenvector over here. But over here for the second mode, this is your principal eigenvector over here, and it's hard for you to come back to that original mode that you started off from in this case. Okay. All right. So here are the results that you see in the Wasserstein metric for these methods, right? And again, you sort of see orders of magnitude improvement in using the repelling attracting dynamics over here. Right? So when you're dealing with low dimensional situations, they're all more or less competitive with each other. But when you go to say 100 dimensions of this anisotropic mixtures, there's a noticeable improvement in using a sampler that is sort of specifically designed to adapt to this geometry. Okay, so this is a plot on what's happening as your dimension increases from 2 to 100. Okay, so the ACF plots that you see over here show that So usually, even for, especially for samplers that are jumping between modes, you sort of see the ACF plots aren't particularly informative because it sort of thinks that your Markov chain is particularly sticky, right? But even in 20 dimensions, you see that the repelling-attracting HMC has a noticeably steeper drop off in the ACF function, right, compared to the other methods, showing that the mode hopping behavior is also happening like particularly fast. This is unfortunately no longer the case when you go to 100 dimensions, right? But in 100 dimensions, you're still jumping between modes, as the plot on the top right over here is showing you. And these are the trace plots for 20 dimensions and 2 dimensions you see over here. Okay, so hopefully, these experiments sort of, maybe should convince you a little bit that, this method is useful when you're dealing with, multimodal distributions. But something interesting that we observed was what happens when you just consider a unimodal isotropic Gaussian distribution. Right? So in this setting, our target distribution is just the plain vanilla normal distribution with mean zero, identity, covariance matrix, right? So it's strongly log concave, and we're going to do this for 4 different dimensions ranging from 3 to 100. And we're going to generate 5,000 samples after running the Markov chain for 5,000 iterations of warm-up. And the methods that we're going to use in this comparison over here are just vanilla HMC, right, for some fixed epsilon and simulation length L. So over here we choose L equals 20. And we also run the repelling-attracting HMC method with the same epsilon and L, but the only difference now is that we're adding this friction parameter gamma, which we choose to be 0.05. Okay, so any differences that we see between the results over here is something that is purely attributable to the presence of the friction parameter in the repelling-attracting dynamics. Okay, so as before, we're going to compute the Wasserstein metric over here, and when we look at the Wasserstein metric, basically between the repelling-attracting HMC and HMC, there is noticeably no difference, right? So the bottom row over here is plotting the margin of error, which is basically the rate of convergence of this Wasserstein metric. So which is of order n to the minus 1 over d. So in particular, they shouldn't be, because HMC does really well, even especially for this unimodal Gaussian distribution. So I shouldn't see any difference in my sample quality when I look at all samples collectively in this case, right? So the performance is more or less the same, or at least indistinguishable if we look at the Wasserstein metric. But now if we look at the ACF plots, oops. Oh, okay. Well, let me try to pull up the ACF plots maybe when we're done. There seems to be some issue over here. But when we look at the ACF plots, it turns out that the mixing that's happening with the repelling-attracting dynamics is significantly better across all of these dimensions for the repelling-attracting HMC as opposed to HMC, right? And this is, we found this to be pretty intriguing, and we don't have any theoretical justifications for why this might be happening, except for attributing it to the fact that in the first half of your repelling-attracting dynamics, where your modes behave as repelling states, the repelling nature of it is essentially simulating something like a chaotic dynamical system. And because it's so aggressive and is sort of having trajectories that start off in similar places but exponentially diverging from each other, you end up with a Markov chain that is better mixed at the end of the day. So even if you're dealing with just vanilla unimodal Gaussian distributions, there is a certain amount of a case to be made saying that there is a noticeable improvement that you might see if you were to use this in practice. Okay, and the last situation is this sort of setup of the Bayesian neural network, where we consider a Bayesian neural network for classification. So you have this noisy, unbalanced XOR data. And so this one was actually well studied in a recent paper. And if you look at the prediction surfaces, it turns out that there are basically two modes that the posterior distribution of this neural network parameters has. And the repelling-attracting HMC is sort of better able to identify that. So the first one, right, because it's highly imbalanced, your first mode is your classic XOR classification. But your second mode is something that should only take into account this and disregard this information over here. Right? So what you should see in your posterior prediction surface ideally is something that is an unequal weighted mixture of the classical XOR prediction surface and your prediction surface that only deals with the top left. And this is sort of more in line with what the repelling-attracting HMC is sort of giving you over here. So if we were to look at the posterior distributions of the parameters in your hidden layer, the repelling-attracting HMC is actually identifying and sampling from different modes that the HMC hasn't discovered in this setup. Okay, all right. Okay, so I think I'm running, I'm already like out of time, so I'll quickly end with a summary. So we proposed this repelling-attracting HMC framework, right? And I sort of invite you to look at the paper where we talk about extensions to other variants of HMC, like magnetic HMC, non-canonical HMC, and relativistic Monte Carlo. And the sort of main thing that hopefully more people will look into is the benefit of moving away from the confines of the physical analogies that underlie a lot of the computational methodology that we look at, because it sort of enables you to look at harder problems in a different perspective, where you're not sort of restricted to just the ways in which the law of nature behave. And a couple of interesting questions that came out of this is that we were sort of interested in what would happen if we were to look at the no U-turn framework in our setting. So obviously, because it's repelling and then attracting, we want a single U-turn to happen. But again, we don't want too many U-turns to happen, right? So how can we sort of integrate that into this framework? And of course, this is just saying that, okay, it satisfies the bare minimum for it to be a valid Markov chain. Does it give you enhanced convergence rates, especially for non-log concave densities? Is it geometrically ergodic? Things like that. And I think a third really interesting direction is generalizing this beyond just samplers on Euclidean spaces. Okay. All right, so we have code available on GitHub. It's, as you can see, fairly simple. You can run a Bayesian linear regression, right, in just 20 lines. So I invite you to have a look, and if you want to contribute, or if you are having any issues, you can just file a pull request over there. I'd be more than happy to look into it and help out. Okay, so with that, I want to end and thank you for staying on for this long, and thank you for attending the talk. Yeah.
Hey, thank you, Siddharth. Very nice talk.
Excellent, excellent. I do have questions, but I'll let other people ask, otherwise I will take over the whole time, so. Questions for, it's really great, this is very interesting. Any questions from, yes, go ahead.
So what I have always been told is that like for multimodal distributions, nested sampling is like a good way to go. So I was wondering if there's been any comparisons done with this method and with nested sampling.
So we didn't do any comparisons on nested sampling over here. We wanted to particularly look at gradient samplers to compare, because that was sort of ultimately where this fits into the scheme of available samplers, right? I think Tuck is a lot more knowledgeable about distinguishing between where nested samplers can be more effective as opposed to this framework.
Yeah. So the biggest difference is the scale to the dimension for the nested sampling to the Hamiltonian Monte Carlo. For example, HMC is known to scale the dimensionality well, which means that in practice, HMC is effective in sampling high-dimensional target distribution because the scale is d to the 1/4, meaning that as the dimensionality d increases, it's not it doesn't increase the too much computational efficiency. But the nested sampling is not quite well studied in high-dimensional cases, and it's not known. So typically the recommendation for the nested sampling is to apply the nested sampling to moderate dimensional target distributions, but it's not recommended for high-dimensional cases. So I talked with Josh Spiegel about this scalability issue of nested sampling, and his recommendation is to sort of, I mean, in practice, maybe 20-dimensional cases for the target. He said that it's safely effective, but he wasn't sure about even larger spaces like dimensionality 10, 100, or higher. But definitely the HMC is absolutely probably the most effective choices for high-dimensional sampling. But the problem is HMC is not for multimodal sampling. So what C did is to maintaining the scalability to the dimensionality and make it work for multimodal cases.
Well, I guess just to follow up the question, I think it'll be useful for you, I think probably not in this paper, in the subsequent paper, to really just demonstrate and you empirically that, then you don't have to explain to people why it doesn't work, just show it doesn't work. I think that the emphasis here is good. You want to deal with the harder problem, which is the high dimension and the multimodality, right? And you're saying there are methods to handle either one of them, but they can't handle both, and you're trying to handle both. I think that would be a good comparison to make.
Yeah, I think that's a very important suggestion. Yeah. And also I think one of the things that I'm starting to realize more after is that there aren't like enough real world comparisons. It would be interesting to sort of run a very thorough comparison of like existing competitive samplers across the board, not necessarily just nested samplers, but other variants that people see. There are a lot of interesting contributions that we do, the tempering space, and just bring all of them. How
Other questions? Yeah. Online and here, I do have several questions, but Vinay, go ahead.
We can now. I was just going to say that we are more than 10 minutes late, past our time. So we should probably let anybody who wants to leave go. And then,
Always, yeah.
Shauli, I mean, we can keep this thing on while you chat.
Yeah, I think feel free to leave as always.
So
But, okay,
actually, yeah, I do have to jump off to another meeting
okay,
shortly.
thank you.
So
So
yeah.
as long
So
as Sid and the
Siddharth, I mean,
talks
you were
stay there,
saying,
I'd be happy.
yeah,
Okay, well,
yeah.
let's thank Sid again. Yeah,
S-
that's a
yeah.
really good talk. And James, take it.
So yeah, Siddharth, you were saying that you know you were expressing some skepticism as to how long these talks take. Now I hope you're convinced that it
These
Right, right,
talks
right, right.
that is
work.
good.
Yeah, no,
Okay.
Mhm.
yeah, so I was told to sort of go slowly in my
Yes,
conversation
absolutely. Yeah,
through
Yeah,
this. So I
that's
hope
great.
more to move.
yeah.
Yeah, it's terrific. So,
Okay. So I have made Siang. Let me also
yeah.
make you a co-host, Siddharth, so you can stay on.
Okay, just
I
Sid,
will sign off.
talk if you have a few minutes, I just have quite a few questions
Yes, yes,
Yeah.
yes, yes.
Bye.
Okay, so several thoughts. Particularly say when you talk about the SCF, right? And in the normal case, and you're saying those things obviously works significantly better. It reminds me, and Tuck knows this work. It reminds me that interweaving strategy Yaming and we worked on, which is also coming from this group. Which what we did is essentially you have two MCMC, right? You have two MCMC, and you interweave them in a particular way. It's more complicated than say just run one, jump to the other one, going alternating. It's a slightly more complicated than the alternating. In that case, what we were able to prove, because these two chains, they go two different directions. That one is we call the sufficient, and the other ancillary. They actually can mathematically show they are actually start to break down the correlation. You can actually have the inequality to show that ACF had to be necessarily going down. But so that reminds me, because you have this, one way to think about it, you have this, repelling, then attracting, right? But from the correlation perspective, it's almost like it's the reverse. Is you have attracting because next one start repelling. And I wonder whether there's actually some mathematics you can do to actually show that ACF has to go down. Because, intuitively it has to, right? Because you're moving it, we're coming here. But that's one thought.
Oh, that's very interesting. Well, so you're talking about the autocorrelation function, right?
Yes, yeah, horticulture, yeah.
Yeah, intuitively, if you move away and coming back, then definitely the not definitely, but intuitively autocorrelation time may decrease compared to the traditional HMC's the circular relationship.
Right.
Um,
But what I'm saying is that there might be some mathematics you can do you can actually show formally. You can show some inequality, right? Because these random variables are because of the. I don't know enough because you need to solve equations, so I'm not sure how it could. But in the other interweaving strategy we did, we were able to show, and it was just took us a year to realize how to show it, but we were able to show it in the end. And so so that's one thing. Related to that, I was wondering, when you have these two, right? What if you do two things? You're doing sequentially, right? You do the this balancing thing. But what if is there some version which you do parallelly? You run the anti-chain, run the other chain, and somehow moving around. Is there any scheme there could do better?
Yeah, it's an excellent suggestion, and I've often wondered that myself. I know, and I think I will have to sort of look into the references that you're mentioning, where you're sort of interleaving these chains with each other. At least intuitively, the way I think about it is that
Yeah.
there is this sort of like a ghost sample that lives in your space. So one that's going in the repelling state and one that's doing the attracting dynamics, and somehow you're sort of coupling them together with this
Yeah,
with
exactly.
this
That's come
momentum
on.
procedure. I don't know how to sort of formalize that and talk about it, but I think that intuition is definitely right. That there should be a way of sort of using this information or transmitting that information in some way.
Yeah, yeah. And that's also, in the most recent issue of Statistical Science, there's a long review article about antithetical sampling, right? You purposely created negative correlations between different runs, right? And I wonder, this is actually another form of, this kind of, broad idea, but in this Hamiltonian way of doing it.
Yeah. That's right. That's right. Um, and yeah, I'm thinking in terms of like the ACF and correlations. There may be some way of bringing in like so ultimately you start off at some position, you sample a Gaussian, so there's some randomness in that Gaussian, and then now you want to talk about the propagation of chaos that happens along this differential equation.
Right.
uh, I think you'll have to sort of use more sophisticated mathematical machinery for
Yes.
that. But I think I wouldn't be surprised if that intuition is right, that the ECF definitely is contracting.
Yeah, that'd be. And now the other thing is just going. This is when I was initially reading your article. I was wondering this: since you already have you have left the real physical world. Why don't you go even further? Because you added this gamma term. You have a matrix there. Well, what if I just put down a full matrix there? And again, my way of thinking is always thinking about mathematically, right? We may prove that the best one is having 3 zeros and 1 corner, but in broadly, why not having, at least simulation wise, you can just explore that fuller matrix. Now it may have not any meanings anymore, but since we're leaving that interpretable world anyway, and it just mathematically explore, I guess it's more than, you're still creating a joint distribution, right? In this Q and P, but now you're exploring a much larger space. Now you may lose all kinds of intuitions, but if it works, who cares, right?
Yeah. So that intuition,
Yeah.
some people have actually done that, where what they do is the differential equation that I was showing you on the screen,
Yeah.
right? Where there's this particular form of gamma, there's that omega
Yes,
matrix,
yes.
which is
Yeah.
that which has that symplectic information and all of that. So what people do is they say that, okay, those are just two matrices. We don't have to, we're not constrained to use them as is. We're just going to replace them with two other arbitrary matrices. And what we're going to do is we're going to train a neural network that's going to
Oh,
learn
I see. I see. Okay.
that's going to learn the entries of that matrix, and it's going to generate samples efficiently. So it turns out that actually sometimes it is actually able to learn those parameters in a way where it accelerates in low density regions and then it decelerates in high density regions. So
I see.
but the issue with that is that you need to train a new neural network for every single problem that you have.
Yeah.
So if you have a target distribution for, say, problem one, then I need to train a neural network, learn the parameters of the matrix, and then generate samples. And then for a second problem, you need to go through that same procedure again. So that's the first problem. The more troubling issue with that methodology is that uh, so remember, I told you in the acceptance probabilities, you have those three terms over there.
Cancellations. Yeah.
Uh, that Jacobian term is really, really expensive to compute because essentially you're looking at uh, a D by D matrix of partial derivatives over there, and then
Yeah.
taking the determinant of that matrix. So if you have this neural network, you need to keep computing Jacobians for every single state that every single proposal that you make in order to do the accept or check step. So, so in that in the paper, it's by Joshua Sol Dickstein. I think he's in Google DeepMind, maybe. So in that paper, they come up with like different strategies by saying, okay, we're only going to look at upper triangular matrices because they're computationally easier to work with and things like that. But again, like all of that comes at a certain price, and I think at least as far as this framework is concerned, we're departing from the physical analogy, but we're still very much inside the mathematical framework that makes Hamiltonian systems attractive. Right?
Yeah, yeah.
So that symplectic structure is what turns out to be is really important and crucial for efficiently generating samples.
Yeah, no, that actually I haven't thought about doing go full speed using this machine learning approach, which I can see that you're absolutely correct. I was more thinking about just to do within a mathematical framework, right? You introduce a little bit more parameter. Now you're right. You need to cancel those things, but in the grand scheme of things, you don't need to cancel them one by one. You just need the entire numerator cancel entire denominator. There's some clever thing you can do actually is cross. Sometimes you can introduce things just cross the right. So all you care is the whole thing it cancels. It doesn't have to be. I know that's much harder, but sometimes when you expose to mathematics, maybe there's a very clever way of putting things in that probably unlikely, but it's just a thought.
Yeah. And I think a preliminary answer that I can give you about this is that there are people who are mainly from the physics background where so at least the way in which I presented the Hamiltonian Monte Carlo was the way Hamiltonian systems work for mechanical systems, right?
Yeah.
Those equations of motions are very different if you're dealing with magnetic fields and fluxes and things like that.
I see.
So where you have like a curl, there's like a cross product that shows up. So all of that manifests in the structure of those omega and gamma matrices. And I know that some people have looked at it for the omega matrix. The omega matrix is just a skew, uh, a 2D by 2D skew matrix, right? Like you have minus I and plus I in the off diagonal elements.
Oh, okay.
But over there, you can sort of make it arbitrary block matrices over there, and then
Okay.
and and they've exploited some structures like okay, your diagonal matrices can be anything, but your off diagonal matrices have to be the negative of each other and things like that.
I see. Okay, that's interesting because you're saying there might be some other physical system, not mechanical ones, can motivate those things. Yeah, I guess. It's great. Okay, that's probably enough. And from me, any questions?
May we ask one
Yeah,
question?
sure, go ahead.
So first off, thank you very much. It was a really cool talk. I wanted to ask him, because just from the intuition perspective, when you were showing those simulated paths, essentially, there's essentially this point where the particle slams into a friction wall, right? Because you suddenly switch from positive gamma to negative gamma. Would it technically be feasible to say we kind of slowly ease off that and then introduce the positive friction?
Yeah,
You know what I'm saying?
that's an excellent point, and this is what we were thinking of considering in the generalization of this. So the reflection that you see that happens, right? I mean, that's sort of effectively that's the phenomenon that we're referring to. So that's happening because there's a sudden transition that happens at t over 2, and the sharpness of that transition can be alleviated by instead of considering just a constant friction parameter that stays the same across your simulation length. What you can do is you can make your friction parameter itself depend on time. So it's like in the beginning stages of your algorithm, you have high friction. So you want to make your samples go as far away from the nodes as possible. But then once you've done that, you want to sort of ease your friction to zero and then start to negated. Does
Yeah,
that
that's
kind
kind
of,
of what I was thinking.
yeah.
Exactly, that's exactly what I was thinking.
And the way in which you have to do it has to be exactly symmetric.
Yeah.
So the positive negative friction, if you plot it as a function of time, you can sort of see that it's sort of like this a square waveform, right? Like it's negative for the first half and then suddenly becomes positive. You can sort of come up with like a sigmoid function and things like that, and you can sort of play around with that and start to. And it turns out that actually, like easing it the way you described it, actually leads to better numerical stability because when you decrease the friction in lower dimensional spaces where your your gradient is extremely unstable, it's sort of like you're not taking a very large step in the wrong direction. That's sort of
Well, thank you, Sid and Talk. I think this is definitely a good direction to explore, and I can see lots of ideas, and you're really solving some really hard problems. So, congratulations, and I hope you publish in the right place, which is important. And,
Thank you.
yeah, thank you, thank you,
Thank you
Talk.
so much, everyone, for sharing your insight, Shelley,
Yeah,
especially.
okay,
Thank you.
okay, all right. Thanks, Talk.
Yeah. Bye.
Talk, I will read the other piece, okay?
Yes. We are waiting for your response.
Okay, yeah. I'm going to DC tomorrow, and but I try to maybe do some reading on the way back, flying back. Okay.
Yes. Thank you so much.
Sure, sure.
Thank you so much, Sid,
Okay,
as
bye
well.
bye. Bye
Thank
bye.
you, everyone. Have a nice day. Bye.
Yeah. Thanks again. So beautiful, beautiful work. Yeah. These are exciting work.